Hello, my name is Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering. And in this lecture, I'm going to introduce the concept of pipelines. And so we're going to work with this concept, we need to go back to our microarchitecture design. And when we last left our microarchitecture, this was sort of what we finished up with. And this is a digital machine that is fully able to execute AVR machine language. And that's fine. So we were able to get a certain level of functionality out of this design, but now we want to make it go faster, right? So much of the activity in the microarchitecture design space deals with how to make our computers faster. And there's a whole bunch of really sort of interesting and innovative design concepts around doing this. And pipelines are an important one, and that's the one that we're going to be dwelling on in some detail. So to start out with, we've already seen in our discussion of microarchitecture design that this design executes one instruction per clock cycle. And so we've got clock inputs here and here. And to kind of better understand this, I think it's useful, and it's going to be particularly useful for our pipeline discussion, to divide what happens in our microarchitecture during each clock cycle into a series of sections or segments. So let's think about what happens at the rising edge of our clock. Well, as soon as we get a rising clock edge, the first thing that happens over on the left here is that our program counter gets updated with a new address. Now, as soon as the address changes, the address is going to propagate along this bus, get read in by our instruction memory block, and a new 16-bit machine language instruction is going to be read out of the instruction memory. And so far what I've drawn here, I'm going to refer to as the instruction fetch or fetch stage of our microarchitecture, or of our, let's say, of our machine language command execution on our microarchitecture. So the next thing that happens is our machine language instruction, gets split up in various ways. It goes up to the control path, and it gets split up in various ways. And through the control path or through the contents of the machine language instruction, we determine some register address values, or register index numbers if you like, that are applied to the A1 and A2 inputs on our register file. Remember that our reading from our register file is just uses combinational logic, so we don't need a clock cycle to read from the register file. As soon as we change our A bus values, the corresponding outputs will show up on RD1, RD2, and RD2 upper. And this much of our instruction execution, so changing the addresses and then reading the register values out on our read buses, I'm going to refer to as the decode instruction / read register stage. So we decode our instruction with our opcode on our control path, and we read our register values. Now, what happens next is the values in our registers are fed into the inputs of our ALU. Not for all of our instructions. Sometimes our values bypass the ALU, but for now, let's assume that these values are computed by or required by the ALU, and the ALU is going to do some work for us. So we feed some values into the ALU, we specify our mathematical operation with ALU control, and we get a result at the output. I'm going to refer to this part of our execution as the execute ALU or exec stage. Once we've done finished work with our ALU, the value can propagate out, but we also need to account for the stage where we do something with our memory. And so sometimes we will take our register values and bypass the ALU and feed our address bus on our memory to either read or write the memory. This part of our execution I'm going to refer to as memory read-write. And then the final thing that we do in our machine language or in our microarchitecture is we take either the result of our ALU calculation or the result of our memory read, feed it all the way back, and write it potentially into a register. And I'm going to call this the write back result, or register write back stage. So another way to represent our instruction kind of propagating through our microarchitecture is with a bit of a timeline diagram. And so you can understand the horizontal axis on this diagram as time. And from this point to this point is one clock period. So imagine at the start, we've got a rising edge on our clock and down, and then on this other boundary is the next rising edge on our clock. I didn't draw that very well, but whatever. And so at the start of this rising edge, the first thing that happens is we start our fetch command. And our fetch command takes a certain amount of time. So we're fetching a new machine language instruction from instruction memory. Once we're done that, once that instruction is available, then we need a little bit of time to decode the instruction and read values from the register. Once we've read values from the register, we need a little bit of time for our ALU to perform the calculation. And we also need a little bit of time to access our memory. Now, in the very simple microarchitecture that we've designed up until now, we don't, we either use the ALU or we use memory. We don't ever use both. We don't need the ALU to first finish its work before we can start accessing our memory. But there are some microarchitectures that do require the ALU to do a little bit of work before we access our data memory. So for example, the ARM microarchitecture has a register that holds your address, just like AVR. But then you can also optionally add a little offset in the machine language instruction that needs to be added to the register before you can access memory. And the ALU does that addition. And so even though in this, in our discussion of pipelines, I am going to continue to refer to the AVR architecture. I'm going to still use AVR assembly language instructions and machine language instructions in our example, but I am starting to move this discussion a little bit more towards architectures that are more sophisticated than the AVR. The AVR microarchitecture does use pipelining. It uses a simple two-stage pipeline, and you'll see what I mean by stages as we get into the lecture. But I'm going to, even though we're using AVR machine language, I'm going to start representing this microarchitecture like it was a little bit more sophisticated than our AVR design. And so based on that, I am going to represent us as requiring a little bit of time for ALU instruction or execution before we can access our memory. And once we've finished our memory, we will write our results back into the register if appropriate. And you might notice here that, I am allocating time for operations that might not necessarily always happen. So for example, if we're just doing a register calculation like add, we need to fetch our instruction, decode our register values, execute our command in the ALU, and then write back to registers. Like we don't have to allocate extra time for the memory rewrite in that particular case. But I'm drawing it this way because this represents worst case execution. So when we're designing our pipeline, we're assuming the worst case, most complicated, slowest possible machine language instruction, where we have to fetch the instruction, decode the registers, do something with the ALU, then wait for memory, and then finally write back to our registers. As is the case with all important engineering problems, we can understand the concept of pipelining by looking at the problem of baking cookies. And so let's say, to introduce the idea of pipelining, let's say we have to bake a batch of 3 cookies. And for those of us who have made cookies before, we know that there are several stages involved in the making of cookies. And for the purposes of this example, we're going to have 4 stages. The first thing we have to do is mix the dough. That takes 10 minutes. We then need to bake the cookies. That takes 12 minutes in the oven. We then have to cool the cookies on a rack. Let's say that takes 20 minutes. And then once the cookies are cool, we pack them into a box. That takes 12 minutes. You might say that's a long time to pack cookies, but let's say maybe this is for a special occasion, and we're like putting it in some kind of fancy box. Anyway, one way that we could organize ourselves in order to make our 3 batches of cookies is as follows on this timeline diagram. So this is a timeline diagram. The horizontal axis is time in minutes. And if you add up all of the stages involved in making cookies, the total is 54 minutes. And so we could start by mixing the cookies. Once the batter is done, we could put it in the oven. Once the cookies are done, we could then put them on the cooling rack. Then we could pack them in the box. Great. Then once they're all packed up, we could mix the second batch, bake them, cool them, pack them, and then mix the third batch, bake them, cool them, pack them. In the end, it's going to take 162 minutes to bake our 3 batches of cookies. Okay, so this is obviously wasteful, right? So while, I'll just get rid of these check marks. Once we have our first batch of cookies in the oven, we're not doing anything, right? So while the first batch is in the oven, why not bake the dough, or why not mix the dough for the second batch? So there are things that we could be doing while other stages of our operation are going on. And the only constraint that I'll put on this problem is we can't do 2 identical stages at the same time. So let's assume that we can't fit 2 batches of cookies into our oven. It's not big enough. There's only one of us, so let's say we can't mix dough for 2 batches at the same time. We only have 1 cooling rack, so we can't cool 2 batches at the same time. And the same thing with the packing. Let's assume, again, we're doing like a fancy job. We've got cellophane and I don't know what else. And so we can't really handle, packing 2 batches of cookies at the same time. So the 2 batches can't go through the same stage at the same time. But otherwise, there's ways that we can improve the efficiency of this cookie operation. And before we get to our next timeline diagram, I'm going to introduce 2 metrics that we're also going to apply to our microarchitecture designs as well. The first one is latency. And latency is the time required to perform a single machine language instruction, or in the case of our example, make a single batch of cookies. So as you may have guessed, baking a batch of cookies is analogous to performing a single machine language instruction like load word or add or something like that. The next metric we care about is throughput. And throughput is basically the number of instructions performed per unit time. And usually we express this in terms of clock cycles. So how many instructions do we perform per clock cycle, or how many instructions do we perform per second? Our single cycle microarchitecture always performs one instruction per cycle, but our cycles are very, very long. So the number of instructions performed per second is relatively small. For our cookie analogy, throughput is also, we understand as the number of cookie batches we bake per unit time. And so for our single cycle cookie operation, latency is 54 minutes. That's how long it takes us to bake a single batch of cookies. And our throughput is one batch every 54 minutes, or in other words, 1.85 millibatches of cookies per minute. And again, this first example you can consider basically the same as our original single cycle microarchitecture design that we showed up here, right? So we have to do all of our operations in a single clock period before we can move on to the next operation. So we have to bake our entire batch of cookies before we can move on to baking our new batch. So if we look at our diagram down here, we can imagine our clock as having a rising edge. We start baking our cookies, we do all the stuff necessary to bake the cookies, and then the next rising edge of our clock happens here, and so on, and so on, right? So we're executing one instruction per cycle, but our cycles are very long. Okay, so now let's look at a way of going a little faster. So as we suggested, it's kind of wasteful to just be doing nothing while the cookies are in the oven. Why don't we mix our dough? While one batch of cookies are cooling, why not get the other batch into the oven, and so on. And so we can create a new timeline that looks like this, where we sort of jam things together. And so again, our constraint is that each stage in our process can only process one cookie batch at a time, so we can't have two batches cooling at the same time, for example. But otherwise, we can allow our stages to overlap. And so here's how we understand this diagram. First of all, in our first batch of cookies, we mix the dough, we bake the cookies, and then while the cookies are finishing baking and starting cooling, we can start mixing the next batch. We can bake them, and then we arrange our baking stage so that as soon as the first batch is finished cooling, we can put the second batch on the cooling rack. While the second batch is cooling, we can be packing our first batch. We can also start mixing and baking our second batch, and so on. So you can see that we're doing things in a way where we're sort of doing things in parallel. And I hesitate to use the word parallel because pipelining is not about having multiple copies of our hardware, right? So we don't have two ovens, we don't have two cooling racks, we don't have two mixers or two packing stations. We only have one. Pipelining is all about using one stage while another stage is busy. But there's still, remember, there is not three parallel sort of cookie operations going on here. We still only have one stage. We've just got three batches going through our single stage at the same time. And you'll see more about this. You'll see what I mean as we continue with this discussion. But anyways, this diagram shows, sort of how tightly we can pack our operations. And so if we do a latency calculation for this example, our latency hasn't changed. So it still takes us the full 54 minutes to bake a batch of cookies. And so this isn't going to help us bake a batch of cookies faster. However, it is going to allow us to start finishing cookie batches at a higher rate because we get started on the second batch before the first batch is finished. And so our first batch finishes at minute 54. Our second batch finishes at minute 74. Our third batch finishes at minute 94. And so while our latency stays at 54 minutes, we're now cranking out one batch of cookies every 20 minutes. And so we've gone from 1.85 millibatches of cookies per second to 50 millibatches of cookies per second, which is a 27 times improvement. And that's significant. One last enhancement that we're going to make to this sort of cookie operation is we're going to sort of give it a bit more of a regular time structure. So if you look at this timeline, we're kind of strangely sort of jammed in here. We're sort of making transitions between stages at kind of irregular times. And so the final version of our design is going to be one where we kind of spread things out a little bit in order to make sure that our transitions between stages occur at regular intervals. And probably you can understand why we're doing this, right? Because this analogy is moving towards being implemented in a computer, and a computer runs on a clock signal. And so any kind of changes that we have in our system has to be done on sort of a regular at a regular clock period. And so what I've done with our example here is I've changed it so that our transitions between stages occur every 20 minutes. And so we, in the first 20 minutes, we mix some dough. In the second 20 minutes, we bake the first batch and we mix the second batch. In the third 20-minute interval, we cool the first batch, we bake the second batch, and then we start mixing the third batch. In the next interval, we're packing the third batch, and at this point, we finish our first batch of cookies. The second batch is cooling, the third batch is baking. Then our second batch is finished in the next interval, and our third batch is finished in the next interval. Now, because there's a couple observations we can make here. First of all, there's no accident. The fact that our intervals are 20 minutes long is no accident. So our clock intervals are defined by the length of our longest stage or our longest operation. And so in this example, that's cooling the cookies. So cooling the cookies takes 20 minutes. That's longer than any other stage. And so if we want to have sort of a regular clock that defines when we transition between our stages, that clock has to give the longest operation enough time to finish. And so because of that, we've basically assumed that we've given every single one of our stages 20 minutes to finish. And so even though mixing doesn't take 20 minutes, we've given it 20 minutes. Even though baking doesn't take 20 minutes, it has 20 minutes as well. And what's happened is that we see an increase in our latency. We've gone from 54 minutes to 80 minutes. However, interestingly, our throughput has not changed compared to our first example. So we're still finishing one batch every 20 minutes, which is 50 millibatches of cookies per minute. And it's really throughput that is the primary, kind of our primary concern. I mean, we have to keep an eye on latency, but throughput is really what matters. Because if you imagine these cookies are now the instructions in a computer program, Sure, the very first instruction you feed into your processor, you do have to wait the latency in order to get the result. But then throughput tells you how many minutes you need to take for your next instruction and your next instruction, right? So you needed to wait 80 minutes for the first batch, but after that you only need to wait 20 more minutes for each of the batches to come out. And we're making billions of batches of cookies, right? All at the same time. And so throughput is really the most important metric. And it's important, again, to note that basically now, if we want to think of this in terms of a clock, our clock now looks like this, right? So the rising edges of our clock mark the transition between stages. And so our clock period now is 20 minutes. And when we go back to our original example, our clock period was equal to 54 minutes, right? And so this is going to be something that we're going to see when we actually implement this in our microarchitecture. So our single cycle microarchitecture, where we have to fit every single operation between the rising edges of our clocks, results in a very long clock period, right? We've got to wait for everything to finish before we can have our next rising edge. If we move to a system where we now have an earlier stage start on the next instruction while the current instruction is still finishing, then we reduce our clock period because our clock period is now defined as, or we now place our rising edges at the points where we make a transition between our stages. And so I'm now going to sort of migrate this example into talking about our microarchitecture, but hopefully this kind of sets the stage. Like basically, when we step back and we look at this big picture, what we're trying to do is we're trying to improve our throughput by getting started on the next instruction before the current instruction finishes, because we've got stages that are idle. So that's basically what pipelining is all about. Okay, so now let's start moving away from cookie baking and get into microarchitecture design. So we've already talked about that our processor has to complete several stages per instruction. We have to fetch the instruction, we have to decode it and read from a register, we have to execute something with our ALU, we need to do a data memory operation, and then potentially write something back to a register. And this is a simplified diagram of our microarchitecture. And we've already talked about how these this kind of ripples through our microarchitecture. So, the first thing to happen is we fetch an instruction from our instruction memory. And once that instruction exists on the read bus for the instruction memory, that's when the registers are read, the ALU executes, the memory is done, something is possibly written back. But during the whole time that we do these other stages, our instruction memory is not really doing anything, right? Like it fetches its instruction, and after that, its job is basically to hold its output stable until everybody else finishes. Now, if we could add a little bit of digital hardware that would hold that output stable, that would just sort of freeze that output or lock it in place, then in theory, we could get the instruction memory started on fetching the next instruction. As long as this point remains stable, if we could lock it or freeze it in place, then the instruction memory could get to work on fetching the next instruction. And that's basically how pipelining is going to work. We are actually going to add registers at intervals throughout our microarchitecture to sort of freeze the outputs. And once those outputs are frozen, it's going to allow each stage to get to work on processing the next instruction while the other stages finish up what they need to do with the current instruction. And that's what I've drawn here. So this is a modification to our microarchitecture to enable pipelining. And so essentially what we've added are these structures that I've shown in gray here are what are known as pipeline registers. And pipeline registers basically freeze the output of one stage so that it remains stable for the next stage. And so at the rising edge of our clock signal, every time we hit a rising edge, these registers are going to take their inputs and lock them in place, freeze them, until the next rising edge of the clock signal. Of course, there is a little bit of extra time that we need to allow because these registers have a little bit of propagation delay as well. So anytime you add logic to a chain like this, you add a little bit of extra propagation delay. So that's something called sequencing overhead. But again, the purpose of these registers are to freeze, in the case of this first pipeline register, the purpose of this first pipeline register is to freeze the output of the instruction memory so that the instruction memory can start fetching the next instruction while the register stage still works on the first instruction. One other modification that we make to our microarchitecture is to add an inverter to the clock input of the register file. And that means, in our original design, a register was always written on the rising edge of the clock. Now we're going to, with the addition of this inverter, the register is going to be written on the falling edge of the clock. And this is basically to make it compatible with the pipeline registers that we've added. And so I'm going to number these pipeline registers. Let's call this first one register 1, 2, and I'll call this other one 3. Now on the rising edge of our clock, 1, 2, and 3 freeze their values, right? And so this input is stable. These outputs to the ALU are stable, and so that means we can change these input values all we want, and the ALU is not going to be affected. And this value is stable as well. And so if we are writing something to the register, that's going to occur here. So register write occurs here. And it is possible that when we write to the register, these values at the output of the register bus feeding into the ALU are going to change. But that's totally okay because register 2 is still frozen. And so we can have changes occurring to the register file, the inputs to the ALU can be changing, but none of that is going to show up on or at the actual ALU inputs because of pipeline register 2. And once that all settles, the register write is finished on the falling edge. 1, 2, and 3 will update their values on the next rising edge of the clock. And so hopefully you can see that this, the purpose of these pipeline registers is basically to freeze the output of each stage, allow the stages then some freedom to kind of change and update without sort of confusing what's happening further on down the microarchitecture. And again, I'm going to be showing you more and more diagrams to show you this in different ways, and so you can get used to this idea. Okay, so with all this in place, we can now we can do sort of our first example. And so what I'm showing here is a very simple AVR machine or assembly language program, 3 commands. We are going to load a value from data memory into register 19. We're going to do an add operation, and then we're going to do store. Okay, so in this diagram, I've shown 3 sort of repeated copies of our simplified microarchitecture, as well as our clock waveform. And so at the start of this diagram, on the very first rising edge of the clock, our instruction memory is going to fetch the machine language code for the load command. Then on the rising edge of our next clock, what happens is our pipeline register, this one right here, is going to freeze the results of our fetch in place. So during this first clock cycle, the fetch has occurred. You know, there was some instability at the output of our instruction memory as, you know, things settled out. But by the end of our clock cycle, the output of our instruction memory is stable, and we are going to use this first pipeline register to lock the result in place for our next clock cycle. And so once this result is locked in place, then the instruction can proceed into the register file stage, and we can read the values from our register file, and that just kind of goes as normal. However, now that we've locked our machine language instruction in place, the instruction memory isn't really doing anything anymore, right? Like in our old single cycle design, the whole purpose of the instruction memory, once the instruction was fetched, was to just hold everything stable so that the stages that followed in the microarchitecture could do their work. However, the pipeline register is keeping things stable, so we can set the instruction memory stage to work on the very next command. So what we're going to do now is, on this rising edge of our second clock cycle, we're going to let the instruction memory go ahead and fetch the machine language code for the next instruction. So it's going to start working on the add command while our register is still reading the register values for our load command. Is this a problem? It's not, right? Because certainly as we fetch the add command, the outputs of our instruction memory, it's going to change, it's going to be a little unstable. But because our pipeline register has locked the value from our previous read in place, it shields us from all that instability. And so during this second cycle of the clock, we can be reading the registers for the load command and loading the machine language instruction for the add command. Now at the rising edge for the third clock cycle, what happens is right at the end of the clock cycle here, everything will be stable again. So the values for the load that we're reading out of our register will be stable. The instruction memory fetch for add will be stable. And then what we're going to allow to happen is the read outputs for load are going to be frozen in place by this pipeline register. The instruction memory fetch for add is going to be frozen in place by this pipeline register. And then, because the instruction memory isn't doing anything anymore, we can allow this rising edge to get the instruction memory to start working on fetching the next command. So what does this mean? Well, the register values that we read over here for load are now being worked on by the ALU. The instruction memory value for add is now fed forward to the register stage where we're going to fetch the registers required by add. And the instruction memory over here is going to be put to work fetching the machine language for the store command. Now, you'll note that our AVR load command actually doesn't require the CP or sorry the ALU for anything, right? We don't really have an ALU component to our load command. And so what's going to happen is this value is just going to bypass the ALU. However, we still need to allocate time for it just in case we're processing a command that does use the ALU. So at this point, I've got red all over this diagram, and you're probably wondering like, well, what is going on here? So at this point, it's very important to think back to the cookies. Think of the instruction memory stage as mixing the dough. Think of and I'll just clear out my diagram a little bit here. Think of the instruction memory phase as making the dough. Think of the read register phase as baking. Think of the ALU phase as cooling. And so if we get rid of all of this red, in this stage, we're mixing the dough for load. Okay. Now, once we get to the next cycle, the dough is ready for baking. The cookies are ready for baking for load. So this stage is bake load. This stage, now that we're waiting for load to bake, we may as well get to work mixing the dough for our next batch of cookies, which is add. So mix for add. Now, in our next cycle, we finished baking load, we finished mixing add, so we just slide everything down. Let's cool down load. Let's bake add. And let's start mixing the dough for store. That's all that's happening here. So we're just feeding one command in after the other once they finish in each stage. And the whole reason why we can divide our microarchitecture into stages is thanks to these pipeline registers that freeze things in place so we can get to work on something further up the chain. But definitely, pipelining is not a straightforward concept. So if you are still uncertain, pause the video, rewind, think about this, post questions in the discussion forum if this isn't quite clear. But I really find that as long as you keep thinking about cookies, as long as you bring it all back to the cookies, you'll get sort of the fundamentals of what's supposed to be going on here. So at this point, a question that you might have is, okay, I'm following this whole pipeline business. How has this actually made things faster? Well, it's made things faster basically by shortening our clock period. So you'll remember in our original processor design, the clock period had to be long enough for us to fetch our instruction, read our registers, do something with the ALU, do data memory, and then write something back to the registers. Now, our clock period only has to be long enough for one of these stages. So we just need to be the length of our clock is basically as long as the longest stage in our microarchitecture, whether it's instruction memory fetching, registers, ALU, data memory. For most processors, it is the memory operations that are the longest. And so the maximum duration of our clock would be, in many cases, determined by the either our instruction memory or our data memory stages. The last thing I'd like to do in this lecture is introduce what I'm going to refer to as a pipeline timeline diagram, and that's what I'm showing here. These diagrams are perhaps a more standard way of representing pipeline operation, and while the diagram here was useful in, I think, sort of introducing the concept of a pipeline, when we actually start to talk about some of the details of pipeline operations, and in particular a concept called pipeline hazards, this style of diagram is much more effective. Now, however, having said that, this diagram does take some getting used to, and in particular, there's a pitfall that students often fall into when seeing this kind of diagram for the first time. So it seems like we've now got 3 copies of our microarchitecture, and the way I've drawn them somehow suggests that we've got 3 data paths working in parallel. And that is not physically the case. So in this diagram, we physically still only have one microarchitecture, and one data path. And we're just showing multiple, copies of the data path to explain or to represent how pipelines operate. And so to sort of kick this off, you'll notice that the diagram is divided into sort of segments, I guess, by these dotted lines. Each one of these dotted lines, each one of these segments represents one clock cycle. So you can imagine, our clock waveform. So this first segment corresponds to one period of our clock. The second segment corresponds to the second period of our clock, the third segment to the third period, and so on. I don't, in sort of future diagrams, when we start to use this sort of diagram format, I typically won't draw a clock waveform here, but sometimes I will draw numbers. So I'll draw a number 1 underneath this segment to indicate this is what's happening during our first clock period. The number 2 here indicates that this segment represents what's happening with our second clock period, third clock period, and so on. So what I want to do is basically redo our pipeline example that we did with our previous diagram. I'm going to redo exactly the same example with this new style of diagram, and I'm going to flip back and forth between the 2 diagrams. So here we have our first clock period. Actually, let me draw this a little differently so it's not so messy. So in this first part of the diagram, we have our first clock period. What's happening in this part of the diagram is represented in this part of our pipeline timeline diagram. So I'm going to put a number 1 up here to indicate that this part of the diagram represents what's going on in clock cycle 1. Now in clock cycle 1, if we go back here, we can see that the only thing that's happening in our first clock cycle is that the instruction memory stage of our data path is fetching the instruction for the load command. If we go to our pipeline timeline diagram, we can see that next to the load command, we have the instruction memory fetch stage. And so basically the way that you read these diagrams is you take a vertical slice, right? And so if we take the vertical slice that corresponds to the first clock cycle, we can see that we're doing an instruction memory fetch for load. We're doing nothing. We're not doing anything for add, and we're not doing anything for store. Okay, so now let's go on to the second clock cycle. So the second clock cycle over here is represented by this part of the diagram. This is clock cycle number 2. And we can see that the instruction for load has propagated into the read register stage. And we're also doing an instruction memory fetch for the add command. If we go back to this diagram, this is the vertical slice that represents what's happening during clock cycle 2. We can see over here for the load command, we are doing our register read operation. And down here for the add command, we're doing the instruction memory fetch. If we go back here to the third clock cycle, the load has now propagated to the ALU stage, add has propagated to the read register stage, and store is what's going on in the instruction memory fetch. So if we go over here for the third vertical segment in our pipeline diagram, again, I'm going to just chop this out here. We can see that for the load command, we've moved on to the ALU execute stage. For add, we've moved on to the register read stage. And for store, we're at the instruction memory fetch stage. So basically, this pipeline timeline diagram divides things based on instruction. And whatever sort of vertical slice you take tells you the stage that we're at with each one of the instructions that are in our pipeline, if you like. So 3 clock cycles is as far as we can go with this diagram, then we kind of run out of memory. But because pipeline timeline diagrams are just kind of a more efficient, more compact diagram, we can continue on and see what happens at clock cycle 4, 5, 6, 7. So for example, in our 5th clock cycle, we can see that the load command has propagated all the way to the register write back stage. The add command is at the memory stage, and the store command is at the ALU stage. At clock cycle 7, we can see that load is already finished executing, add is finished executing, and store is at the register write back stage. So now if I just clean things up a little bit here. One other thing that I will do on these diagrams is I will use shading to indicate which of these stages are actually active for each of the particular commands. Remember, I mentioned that we allow time for each instruction to execute in each stage, even though not every instruction requires every stage. So for example, with the AVR microarchitecture, the load command does not require the ALU. And so I indicate that by using the shading. So the load command during clock cycle 1 uses an instruction memory fetch. And so instruction memory is shaded gray. The read register, so in instruction cycle 2, the load command is reading from a register. And so I indicate a register read by shading the right-hand side of the register file block. Load does not require the ALU, so the ALU is not shaded for clock cycle 3. And you can think of, if a block isn't used, you can just think of basically a connection, bypassing the ALU and just passing the data on to the next pipeline register. Load does use data memory, so data memory is shaded in clock cycle 4, and load does write to a register, and so the left-hand side of the register file is shaded in clock cycle 5. We can quickly do follow the other commands. Add uses an instruction memory fetch. It reads from registers. It does use the ALU. It does not use data memory, so that's not shaded, and it writes back to a register, so that is shaded. And store uses instruction memory. It does read from a register, doesn't use the ALU, does read from memory, and does not change a register because store is taking a register and writing it to data memory. So, again, go through this slowly. If you need to, pause the video, rewind, make sure that you're comfortable that what I'm representing in this diagram is the same thing that I was representing in this diagram over here. Remember, this diagram is not meant to imply that we have 3 parallel data paths physically existing in hardware. This is the same physical data path. We're just representing it one time for each instruction that's sort of propagating through our pipeline. And once you're comfortable with that, we're going to proceed to the next lecture where we're going to use these diagrams to talk about something called pipeline hazards.